So hi everyone, today I'm going to be talking about basically optimizing computation and data movement for fresher features. So I'm actually going to talk about two projects today. They're both sort of about data or feature freshness. One is, so if we think about like what actually causes data or features to be stale, there's first computational bottlenecks. So basically you might have some new data and it hasn't been processed yet to actually be reflected in your feature values. So the first project I'm going to talk about, ralf, is about optimizing this computation. And then the other bottleneck that we often have is data movement bottlenecks. So because data is slow and expensive to replicate, we end up having stale data or stale features. So this is relevant to the second project I'll talk about, which is Skyplane, which is optimizing data movement for faster, cheaper data replication. So first, ralf, if we think about what a typical feature store setup is, we might have something like a news application, which is sending a query stream to a model, which is using these features. And then these features are maintained by a click stream going through some kind of transformation pipeline, which is doing the feature maintenance. So one challenge here is that this feature maintenance step is often very computationally expensive. So this means that we can't necessarily process every single click if we have a very expensive transformation due to limited resources. But at the same time, if we don't process updates fast enough, like with a streaming system, and maybe we only compute things once a day, then this can actually often lead to model performance degradation as a result of features being stale. So I think some other speakers have mentioned this problem, and there are sort of solutions to it as well. So fundamentally, there's sort of this trade-off for pre-computed features, where on one hand, you can have these very real-time, high-quality features that immediately ingest new data to update the feature values. But then you also have these sort of lower quality, but more cheap feature computation systems. So things like batch systems that maybe just update features in daily batches. So we have this trade-off here, and for any system, we want to be able to figure out basically what's the right point on this trade-off curve. So what we did for this ralf project was actually trying to figure out, like, can we do better than this trade-off by having more intelligent scheduling? So basically, a lot of features are actually never queried. And so then we can actually save a lot of money by our resources by not bothering to update things that are never queried. And also a lot of features, they might have new data come to them, but the feature values themselves may not actually change in any kind of meaningful way. So in these cases, we also don't want to update, basically waste resources updating features, since the staleness isn't going to actually affect the downstream model accuracy, which is what we actually care about. So at a high level, this work basically introduced a scheduling policy where we basically try to minimize something that we call the cumulative regret of a feature. So basically, as the model makes predictions from some incoming stream of queries using the features, we track what is the eventual error that we observe for those predictions. And so for every single key in the feature store, we basically track like how much error have we seen that's been resulting from this feature. And then basically on the feature maintenance side, prioritize what keys that we update based off of which ones has the highest cumulative regret. And then we set that back to 0. And so it sort of ends up balancing resources to prioritize the most queried or the most rapidly changing features. So this is a very high level view. I'd be happy to email the paper draft to anyone who's interested. And the overall result of this is we basically can achieve higher accuracy for the same cost. So by basically prioritizing the features that are the most important to update or the most frequently queried, we can improve the cost accuracy trade-off and basically for the same amount of resources, be able to get higher quality features. So the second project that I'm going to talk about is Skyplane, which is fast, cheap cloud data replication. So part of why we started looking at this project was actually because for a lot of applications, data movement is actually the bottleneck, not compute. So for things like feature publishing or serving, moving all that data can actually be a huge bottleneck. So this happens in cases where maybe you have a single model that needs to access data or features that are spread across multiple regions or clouds, or maybe you have a single set of features that need to be served to different applications or different models that are spread across, again, different regions and clouds. So the reason why this is challenging is because in general, data transfer is very slow. So if you're trying to move data from maybe like one application or one user on one side of the country with like GCP to maybe the other side of the country in a different region on Azure, it can actually be really, really slow. And As a result of this, we can end up having stale data if we have geo-distributed applications or applications across multiple clouds. So a 70 gigabyte data set can take up to 1 hour to transfer with existing tools. And on top of that, we have very, very high egress fees whenever you try to move data between regions or cloud providers. So the cost of moving a 70 gigabyte data set can actually be equivalent to running 34 like M5 large instances for an hour. So this data transfer cost can be really, really problematic if you're trying to move data to keep like all your data sets or features fresh. So the reason why slow transfers are very problematic is because for a lot of real-time applications, slow transfers can mean you have worse accuracy. So for example, if you're maybe like Uber and you're trying to do ETA prediction, as you get new data, you ideally want to be able to process those updates, create new features, train a new model, and then deploy that as quickly as possible. But at each stage, if you're having some kind of bottleneck because of the data movement, especially for something that's as geo-distributed as Uber, you're basically, this whole pipeline is going to take a lot longer just from waiting for the data to transfer. So Skyplane is basically a project trying to solve the problem of managing data transfer across regions and across clouds being very slow and expensive. So we basically have a simple CLI tool that looks a lot like the AWS CLI, except you can transfer between any of the 3 major cloud providers, and it's a lot faster and cheaper. And so, yeah, overall, our results show that Skyplane is up to 113 times faster and up to 3.8 times cheaper through doing compression and bandwidth tiering. So yeah, Skyplane is open source, so you can install it with pip install Skyplane, and then also this QR code will take you to the GitHub URL. So I'll just very briefly go over why transfers are slow in the first place and some of the techniques we use to get around this. So first of all, there's often congestion along the direct path. There's poor peering between providers, and there can also be packet loss from the physical layer. So one of the techniques that we do for this is that basically in cases where the direct transfer between 2 regions is very slow, we can often find overlay regions. So basically some other third region, where if we go through this region instead, the transfer ends up being a lot faster. So here we went from about 2 gigabits per second to about 4 gigabits per second. Another technique we use is striping transfers for large files. So if we have some very large file, we can actually subdivide it and then parallelize it across multiple VMs for the transfer. So this gives us some of the biggest improvements. And then finally, we also use a couple techniques, including compression, to basically compress data as it's being transferred to basically save you egress costs. So altogether, we have up to about like 110x speed up for large files in particular, which can bring transfer times from 2.5 hours to just a few minutes. And then we also save on costs. So if you compare to AWS Data Sync, which is going to charge both for egress fees and also service fees of the service, you will actually go from like $7.27 to $1.17 using Skyplane instead. So all the techniques that we use are covered in the NSCI paper that we have. So I'm happy to email this to anyone who's interested. And yeah, that's the end of my talk. And thank you everyone for listening. And please let me know if you have any questions.